What about now? Got me. Okay, thanks. So my name is Chris McNamara, and I'm here today with Dave Hunt, and we're going to talk about PowerWare packet processing. I didn't move. I honestly didn't move. So we both work at Intel, and we're both in the software group. So I suppose, you know, to kind of level set on why we are here, that and my daughter, she's 7, she asked me what I do. And I didn't really want to try and explain to her what DPDK was, but I explained to her, we make the internet go faster. And she kind of got that. And you know, when you combine that with what we're trying to do with power awareness and energy efficiency, we're trying to marry those two concepts today, albeit them off lofty goals. So we're trying to say, you know, let's save the planet, reduce carbon footprint via DPDK, and also combine that with making things go faster. Okay? So you guys will know very well that the data is going, you know, off the charts. You see 5G coming out. You see wireless broadband in your houses going up. You see those data rates expanding. You can see that firsthand. And we like to think of this in terms of always on. Okay? So what we're trying to do with DPDK is to try and make it more energy efficient and get the best bang per watt. Okay? So we're not trying to just say turn it off and leave it off. It's when it's running, we're trying to zone in on the potential for performance and efficiency. Okay? Now, you guys, and I think somebody mentioned yesterday in one of the talks about continuous polling and reducing those cycles. So a very simple example of some of the schemes that we've implemented is that if you've got a 10 gig or 20 gig or 25 gig NIC or 40 gig, that you could be running 100 megs, you could be running a gigabit, you could be running 5 gigs. So what we're trying to do with DPDK is match the performance in time to consume the appropriate amount of energy. Okay? Now, there's kind of a few business drivers that we have to justify our work somehow, and we look at this through the lens of electricity and cost saving, and as I mentioned, marrying that with performance when it's needed. Now, we took the, I suppose, previous power management scheme and we've refreshed that, and we're close to getting those patches applied on the mail list. So to kind of paint a bit more of that concept and about how we're trying to, I suppose, use DPDK, we put together this graphic that shows over time a 24-hour period. The purple bars are supposed to represent the user traffic on the network. And you see the green bars are, to represent idle time. And you'll see on the horizontal that we're representing the amount of, I suppose, the busy nature of the network. And DPDK being a core element of that network, there are multiple instances of DPDK end-to-end on different nodes, okay? Now, it's an illustration. I'd love to get some real network data, but just for illustrating the concept, when you look at the green bars, we look for the opportunity to turn down the performance of DPDK. So when you're polling, we turn the dial on DPDK in terms of what we do with our CPU, and we turn down the core frequency, which saves energy. Okay? Now, similarly, you can put that into further levels of sleep states or other, energy efficient states, right? But this is just an example for now. When you start looking at, say 6 p.m. towards 10 p.m., you can see that the network gets busy. So this comes back to the dimensioning of the network overall. And what we're showing in this orange, period is that we're going above the busy nature of the network by 20%. So we're saying that we can burst above what the 100% dimensioning. So in cases where you're oversubscribed, you may want to drive up the performance, okay? And what we've pushed in those patches, for example, has been APIs to allow you to turn on Turbo Boost, which is a technology that allows us to turn up the performance of a core, essentially. Now, expected burst, so this comes back to your dimensioning. You might dimension for 100%, but you might say, I'm going to try and maximize my performance given I have power available in my platform for a very short period of time. So you might use this network model as a way to pick how much of that performance you try and leverage, okay? Now, I suppose the elements of a good scheme that we put together were, I suppose, captured by what we have in the bubbles here on the right, which is the ability to monitor. So for us, we looked at stats APIs and being able to get the right statistics off the network cards. But then we need to be able to measure what the system is doing to be able to adjust the power of that system. Okay? So we need to know how much work we have. And the third part of that is the action or the reaction based on, again, what's happening in the system. So you kind of have this, I suppose, a loop that's running on the system that's got to, I suppose, interoperate with these three capabilities. Now, from an always-on perspective, the challenges that we had was we weren't race to idle. So we weren't trying to turn down DPDK immediately when no packets arrived in our descriptor queue. What we're trying to do here is to, we don't have to race to idle, we can take our time going down, but we want to be able to scale up very quickly if we turn down the capability of the server when a burst arrives. So if you put your server to sleep, you want to be able to scale up very fast to be able to get back to your dimension performance, right? So for us, what we looked at was that ability to scale up quickly, which ultimately results in a certain time in a sleep state or a time to change state that needs to be factored into the design of the DPDK application. I saw some trends, and we're going to talk a little bit in a minute about some of the policy-based controls that we see, and Dave is going to walk us through some of the limitations of the scheme and some of the improvements that we've tried to make, and to try and make this scheme a little bit, more usable. Now, so again, I suppose I'll just say that one of the learnings that we had, not only was the time in the queuing, was that the closer to hardware we can make these decisions, the faster it is to react. And it's kind of, I suppose it's a sensible or a kind of a logical thing to say, but it took us time to find that out, right? So ultimately, I suppose where we're going with this is the ability to apply power where and when it's needed. Rather than having a very fixed dimension of power, we want to be able to turn the power controls to meet the use cases that we have. Okay? And as I mentioned, the ability to scale up quickly was a key design consideration for applications using it. And queue depth was one of the, I suppose, the indicators that the previous scheme, I suppose, in a sense, needed to be refreshed because the queue depth is very short, okay? So what the example I picked here was that if you had 128 descriptors, I think that was on 10 gig Intel Niantics, that it only holds about 8 microseconds of data. So if you, as an example, put your server to sleep for 100 microseconds, then you're going to suffer packet loss because you're not going to be able to run, okay? So these are the considerations that we learned that, queue depth, and it's not only on the received descriptors, it's important to say that, you need to identify the modules with shallow queuing to avoid that packet loss. So if you're running your testing and you're looking at your queues throughout your software infrastructure, you need to be able to dimension your system appropriately for your worst case power state, let's say, depending, whatever that is, right? Depending on what architecture you're using. So at this point, I'm going to hand over to Dave, and he's going to tell us a little bit more.
What's the next?
Next.
So just to set the scene a little on some simple measurements that I did recently. What we have here is when we turn down the frequency of all the cores in the system. So this is a very simple use case. Ramping up all 56 cores on a machine, an example machine I have in the lab back in Shannon. And I ramped all the cores up to 100% using Sysbench. It's an old, desktop, but it still applies. So just to measure the kind of energy consumption on my server at the wall socket. So we can see here that at 2500, 2.5 gigahertz, which is the max non-turbo that this system will do. I'm not talking about turbo here. But we can see the almost linear scale down as we scale down the core to 1200. So the bottom light blue is platform, so that's fairly constant. So I measured the difference with turbostat, the difference between what's platform and what's package. So the package is actually scaling down. So between here and there, it's approximately 30% saving if you can scale down your core for a given amount of time in the day. So when you know your network is quiet, or you're measuring that your network is quiet, you can scale down your frequency. Now, you're still handling traffic down here. You're still handling traffic, but at a reduced rate. So it's not like you're handling zero traffic, you're still handling a lot of traffic. And also it's worth mentioning, it's not on this slide, that even going further with, when you start playing with MSRs, you have the encore frequency to take into consideration as well, so you can turn that down. So there's a max encore and a min encore that you can set with an MSR. And when you're at, just when you start slowing down, your encore will trigger down to the lower frequency, and you get a further, you'd almost get a further 10, 15% on top of that 30%. So you could be going as much as 40% saving on your platform. So it's well worth looking at this. And all we're trying to do here today is just suggest that people start looking at this and exploring it using the APIs that were there already. There's plenty of APIs in the Power Management Library that were there already that allowed you to do this. And we're adding a few new APIs that give you a bit faster control for different use cases. So let me see there, example Xeon. So that was on an 8180, a 56 core Xeon. I mentioned the further saving there with Encore and varying core activity. We have, let me see what's on the next slide. So there's two main patch sets that we have in progress, or hopefully we'll get in for 1711. One of them is Turbo, and the other one is this one, in-band policy for power management. So what we're trying to do here is accelerate the speed at which the system can react to changes in traffic. So this is ideal when you want to set thresholds based on traffic load and scale up and scale down. We also have time of day policy. So we're basically sending a policy down through the VirtIO channel to the host. And then from then on, the guest application doesn't need to worry about power management. It's like it's giving a set of rules down to the power monitor, which these applications exist already in the Power Library and the examples application. We're just adding a few extra features into it. This adds a policy download. So the policy can contain information on traffic rates, information on time of day, and information on workload. So for example, there's an array of 24 integers for an hour of the day in the example app, and we just set a threshold that we want the CPU to be scaled to during those hours. So in the middle of the night, we might say we want to go down to 1200, and then during the evening in peak hour when everybody's, when the whole country is awake, we want to ramp it up to maximum power. And even with the new APIs, we can add in, say for 1 or 2 of those hours, we want to maybe turbo up as well, just to, a couple of cores we might want to turbo up just to accelerate some of the bottlenecks. It's basically a way of matching compute to the network CPU load. So you can see here, we have, one of the additions we added in was when we send down a method of reading, fast scale up is a method of reading the stats in the NIC. So we're reading those, so we're spinning on reading the stats direct from the hardware with this power monitor so that we don't need to wait for the guest to send down a request to scale up or scale down. We can be monitoring the NIC stats and just react immediately. So we're knocking off 2 milliseconds of response time that it would have taken in the past to send down this VirtIO serial request. Now we send down the policy and the power monitor in the host can react immediately. Almost immediately, just as long as it takes to read the stats. So we're spinning on reading stats when the traffic is slow so that we can burst up very quickly. Anything else on that? Yeah, so, okay. So the next section was, so that was the policy. So we're still discussing that. That's up on the mailing list at the moment and we're reviewing it. And that's gone through review at the moment. This has been applied already, earlier last week. Thanks, Thomas. So this just adds 2 new APIs into the existing Power Library set of APIs. So the previous APIs were scale up, scale down, scale to a particular frequency, and the guest application could request any of its cores to be scaled up or down or set at a particular frequency. So what this extends that to do is to enable turbo. So what you couldn't predict where your cores were going to go into turbo or not, but what you might want to do is enable turbo on your package and then set all your cores to not go into turbo. So that would prevent them from all, using too much power. You know what you want at 100%. But if you have some bottlenecks that you want, or just some cores that are bottlenecks, say a distributor app distributing work out to cores, you might only want to turbo up one core. So you can choose at a particular time of day to turbo up that core, leave it at that for the hour, for the busy hour, and then to scale back down when that time period is finished. And what I found with some of the research and some of the use cases using, say, the distributor library, the DPDK distributor library, for example, scaling up the distributor core not only increased the performance of the distributor, it also increased the performance of the whole system. Say a virtual machine with, say, 8 worker cores doing work. The distributor was the bottleneck. So, and the workers were almost starved. They weren't running at 100% of what they could work at. So just by turboing up the one core, I got almost 20%, 19.5% performance increase across the whole, that whole VM, because the bottleneck was resolved by turboing up that one core. So as I said earlier, we're suggesting you just take these, play with them, measure, put a watt monitor on the wall, measure your system, try turboing cores, try scaling down your frequencies, just try, the different use cases that you might have. And just see what you get, because I'm sure you could get some good power savings by using those APIs. Have to acknowledge Rory, Nemanja, and Constantine for the reviews. Rory and Nemanja did the policy parts of the patch set. I did the turbo side part of the patch set. And any questions? Question down there.
Have you considered the kernel implementations of power management, and why is it in DPDK?
This is on, yeah. We found from looking at what's there in the kernel today that it wasn't really effective for the low latency approach that we want to take, that ability to scale up quickly. So we found that what's there didn't really work, and the low performance in the kernel really drove the performance of the platform down versus a high performance which took too much power. We couldn't, from the lens we were looking through this at a networking level, that it didn't meet the needs. And the second piece was that we wanted to, I suppose, allow the DPDK users that have that visibility of those packet rates directly, and allow them to make better decisions in user space in the application space versus having a general scheme.
It kind of gave you a more fine-grained control. Like if you're running the Intel P-States driver, you can't really predict, and you enable turbo on your machine, you'll find that when a core goes active, it'll go turbo. And you can't predict what frequency those cores go to depending on how many cores are active. And also depending on how many cores are active, your max turbo will come down in direct relation to the number of cores active in the system. So what we wanted to do was give you something that's predictable, allow you to bring all the cores up to 100% like P1, non-turbo, and then just allow you to selectively core your bottlenecks. Because if you've got one worker and 4 workers and a distributor, if you have all those running at 100%, they're all going to go to a certain turbo frequency. We just wanted to keep those down and just turbo the worker, which gives you better power saving because you're not actually turboing up the workers. They don't need to be turboed. So it gives you more fine-grained control.
When I looked at the performance sample app before, I could see that, as you said, the API was very kind of low level, but the sample app still had a lot of code to try and figure out like when to reduce the power, when to go into interrupt mode. Have you any plans to try and wrap things a bit better? Because I would see that people wanting to use this code, probably some of those algorithms that are in the sample app might be similar towards different applications, and there might be some. If you could make a library with profiles or something, it might be something that maybe could be reused in a simpler fashion from an application perspective. Yeah,
I think that's a good suggestion. I mean, that's something definitely on the to-do list. What we were trying here was just, put the enhancements out there. I mean, the library hasn't been touched in a while, and we've just, got a new interest in it with the per-core turbo. It's certainly an interesting area, I think. And we wanted to add those in, but we know the profiles, they're in their early stage yet. Maybe there is in the future. a possibility that we might do a library based on profiles, but certainly we just wanted to tease it in first and see how people react to it, get some feedback from the community, and then take it from there.
Right, thanks. Is it possible to define metrics other than time of day and queue length to affect power savings?
Yes.
Thank you.
So what we looked at was in some of the prototyping, we developed samples apps, and as David mentioned, we've been very much looking at getting the infrastructure right, the APIs. It becomes, I suppose, a custom scheme depending on what work needs to be done, and one of the examples that we gave was AM and PM. So day and night you could set up a profile on the platform, and then you can monitor packet rates. So what we did is we counted the number of packets that were, to try and detect a burst. And the second piece then was we counted the number of packets that are in a system. So we know how many packets are in the core between RX and TX. And then we use that as a count to dimension the CPU frequency. So there are some, I suppose, drawbacks with that you need to know your worst case for every packet. And in a sense, you end up, if you have a crypto packet and it's just a simple plain text forwarding packet, then you're going to take more compute if you're doing it in software. So you end up with a little bit of waste. So that's one of the examples of the metrics that we looked at.
Can the application define its own metrics, though, that might be based on something completely different?
Absolutely, absolutely. And that's why, as Dave mentioned, that, we looked at making sure the APIs are there so that applications can adjust the power, frequency per CPU, or turn on turbo if you've got busier cores that you need more frequency, which you get with turbo.
Like in the patch set that we've pushed up, all the intelligence or the algorithm, the profile is in the sample application. It's a sample app sending down a profile to another sample application, which is the VM Power Manager. That's one of the example applications. So all that intelligence is implemented as example applications. There's nothing in the library. There's only one extra, I think, I40E thing to read the stats. But apart from that, it's all out in the sample applications. So it's trying not to tarnish too much the
we'd be interested to hear any suggestions that you might have about what else we, could monitor to give us better granularity on that.
Okay. One other quick one. Have you looked at the implication of latency when clocking the cores down on packet flows and all that?
They'd be able to answer that question, but I think the whole reason we went to push this policy down closer to the decision making closer down to the hardware was to just keep that latency down as low as possible. So was there any particular?
Yeah, I suppose there is more latency when you turn down the frequency, as you'd have with a CPU that's running at 3 gigahertz or 2 at 1.5, right? So by turning it down, you do slow the processing down. So
and the difference between trying to scale up, if your decision maker is up in the guest and that VirtIO, that 2 millisecond coming back down to if you had the decision making up in the guest, by the time it's sent down, you'd have a big spike in latency, whereas we're moving all the intelligence down into the guest, so it reacts faster, so you're keeping that latency down. I'm thinking of the transition period rather than, of course, then when your frequency is down, your latency is slightly higher, but it's going to be consistently worse, if you know what I mean.
And that's maybe one of the things that sort of leads back to my original point that, you can maybe define a metric that ultimately is a minimum latency that you want for the system, and that will dictate clock speed as well as load and packet.
So you feed in latency and you say, I want my latency to stay within this, and then it works out the profile based on, that's possible,
Yeah, because the queuing that we mentioned earlier was what we looked at to reduce the loss. And what we saw with the old scheme was that if you were getting, because 8 microseconds is quite a short time, if you were getting any jitter on how the NIC was interfacing to the CPU, then you might get some false positives. And you might scale down at an inappropriate time. And we saw that when looking at the old scheme, that sending a constant traffic rate, sometimes you might see, a power, a frequency change. So
you want to minimize that. You don't want it flip-flopping all the time. You want it to at least get...
You want to do it when it's appropriate for the workload. So, thank you. That was really good.
It's the first time we hear about green DPDK.
Yeah.
Thank you.
Thanks, man. Thanks.
Thanks.